This video is going to look at the chemistry involved in alpha carbons. What we've talked about before with carbonyls is having nucleophiles come in and attack the electrophilic carbon, adding a new bond between the nucleophile and carbon, creating a negative charge on the oxygen. If we have a base, we actually can pull off the hydrogen that is on the carbon next door to our carbonyl. This is known as an alpha carbon because it's in the first position next door, and on the alpha carbons can be one or more alpha hydrogens. After pulling off this hydrogen, notice that we can place a negative charge on the alpha carbon. What's the incentive for this reaction? Well, having that negative charge means we have delocalization if we have the carbonyl group. So again, we're going to be pulling off the hydrogen that is alpha to the carbonyl with a base, placing the negative charge. Now we can also have resonance with the oxygen, creating an alkene and a negative charge on the oxygen. So this is going to increase your stability for that negative charge, meaning these alpha hydrogens are often more acidic than other hydrogens on alkanes. If we have one that has two carbonyl groups, we now have double the delocalization. So we often will see increased acidity for these compounds that have two carbonyls with one carbon in between them. When we have this type of resonance, it's actually called a tautomerism. And you'll notice the difference here being that when we're going from the keto to the enol forms, we're actually breaking a bond with our CH3 group as well as making a bond with our O. So that's the difference between resonance and tautomerization, is that you actually are breaking and making bonds even though this is a going back and forth in a reversible reaction. So these are going to be different in the location of where the double bond is. For most forms, the keto is going to be more stable, having the double bond to the oxygen. There are some exceptions. If you can look at this one here, you actually have the enol form gaining aromaticity, so this is being pushed towards the enol form, somewhat of a rarity. We can draw this equilibrium or this mechanism in acid or base. If we're in base, we're going to start by pulling off your alpha hydrogen, having that negative charge being pushed onto the carbons, pushing the electrons out onto the oxygen, and then having that oxygen with the negative charge pick up your hydrogen. This will give you your enol form and regenerates your hydroxide that you had at the beginning of the reaction. In acid, your first step would be to protonate your carbonyl oxygen. This would allow you to steal that alpha hydrogen a little bit easier because we're incentivized to make another bond to carbon. So we can have our base take our hydrogen, push that bond towards the carbon, and then push electrons out onto your oxygen, making your enol. If we wanted to react a strong base with something that has an alpha proton, LDA is known as lithium diisopropyl amide. You should consider it a bulky base. We can then pull off the alpha hydrogen, putting a negative charge, pushing it down, pushing out, just like we had before. At this point, we know that that negative charge on the oxygen wants to come push back down. We can see that position become nucleophilic. Notice here we have a simple SN2 reaction in which we would be making a new carbon-carbon bond on the alpha position. Notice the difference from what we've seen so far with carbonyls. We've only seen them make new bonds between the carbonyl carbon, not in the position next door. So alpha hydrogens open up the possibility for new carbon bonds at the carbon next to the carbonyl position. The main reaction that this involves alpha hydrogens is going to be an aldol mechanism. Both aldehydes and ketones can undergo these. They are going to usually involve two molecules that are the same. You can have what's known as a mixed aldol, which we would have two different carbonyl group starting point, but the easiest way is to make sure that you have two molecules of the same thing. One of these is going to become your nucleophile, and one of these is going to become your electrophile, and that's where you can see, well, which one would be used as the nucleophile and electrophile. If they're different, it's really hard to push that reaction to take place. So let's look at how this happens. The end result of these will end up being, and I have here aldehydes and ketones, is that, again, your base is going to pull off a alpha hydrogen and end up putting two of these molecules together. You'll notice that the first one is in yellow, the 3 carbons from our original aldehyde. The second one is in white, pointing to the 3 carbons and now what our carbonyl has become in hydroxyl group. Notice the new bond is going to be formed between the alpha carbon and the carbon that was formerly the carbonyl carbon, right? So we're saying in your nucleophile, that's the one that's going to be the alpha carbon. This is known as a beta hydroxyaldehyde because since the first carbon next door is alpha, the next carbon is going to be beta, so we have a hydroxy group 2 carbons away from a aldehyde. The same reaction will take place with a ketone, having a beta hydroxy ketone. And always for all aldol reactions, you need to make sure that you have twice as many carbons as you started with if you're putting 2 of the same pieces together. Let's look at the mechanism for an aldehyde. As with both of these, the base is going to pull off your alpha hydrogen. You have a resonance structure into the enol form. Again, it's going to stay mostly in the keto form. Since we know the top form is what it's going to exist as, we can see that piece acting as the nucleophile for the same aldehyde. Notice here I've drawn it differently, but it is the same piece, right? We have 2 carbons in an R group. So our alpha position is now our nucleophile coming into our electrophilic carbon, pushing out. This should remind you of all the reactions we talked about in the aldehyde and ketone chapter, because all we've done here is change the nucleophile. At this point, you now have a negative charge on the oxygen of your electrophilic carbon. That will then pick up a proton from the water or solvent, and you will get your beta hydroxyaldehyde. You can do the same mechanism with ketone. Nothing changes, right? So you're going to pull off a hydrogen from your alpha position, draw your resonance with your enol form. This piece is now going to act as a nucleophile to another example of the carbonyl. This could be the same or could be different. Arrows are the same. We now will have an O- that can still pull off a hydrogen from water or whatever solvent you have, giving instead a beta hydroxy ketone instead of an aldehyde. The key part is recognizing the first arrows. Once you've generated your nucleophile, your arrows are going to be the same as your other aldehyde and ketone reactions. In addition, rather than have that hydroxy group, oftentimes you will see a dehydration reaction. We talked about these earlier in the quarter, and here we can pull off or remove that OH group by either acid workup or base, putting a double bond there. This is advantageous because we've now created a conjugated system. When you put 2 of these together, it's often known as an aldol condensation because you're putting 2 things together while also removing water. If you want to do base, you can also do that. Base will create your beta hydroxy ketone from the mechanism we talked about earlier. Then base will also remove that alpha position, hydrogen again, creating a double bond. So this would be pulling off, after you've made your beta hydroxy ketone, pulling off the alpha hydrogen that is again still acidic, pushing that electron down. You can go to your enol form, pushing your double bond over, kicking out your OH-. This is only okay here because we are in base. Normally OH- would be a poor leaving group, but the incentive to make a conjugated system is what allows this to happen. If you have a crossed aldol addition, meaning you're starting with two different types of carbonyl groups. So notice here I have a 3-carbon aldehyde and a 2-carbon aldehyde. Well, it's possible that you can pull off either alpha hydrogen from A or B, meaning either A or B can also be the nucleophile you attack with. So if you have a crossed system where you cannot limit where or how many alpha hydrogens you have, your reaction mixture can get complex pretty quickly. A special type of reaction that mimics what aldol happens involves esters. And so even though you haven't seen esters, I like to show you the similarity between the arrows we're drawing between an aldol and what's known as a Claisen condensation. Notice here it starts off the exact same way with a strong base. The end result here is what's known as a beta keto ester, because on the right hand side in our yellow box we have an ester group. On the carbon 2 positions away we have a ketone. Let's look at how this forms. Your mechanism is going to start off the exact same way, pulling off the alpha hydrogen. This is now going to create a nucleophile out of the alpha carbon. Again, I'm using another molecule of my ester here, having that position go and add to the electrophilic carbon. Even though you haven't seen esters, these arrows are the exact same as with ketones and aldehydes. At this point, what makes this interesting and more conceptually difficult from an aldol condensation is, at this point, if the oxygen pushes down, it can actually create a leaving group. Notice the leaving group here is the same as our base that we started out with. We did not have a good leaving group in our aldol mechanism, meaning it needed to stay as an O-, eventually becoming an alcohol. At this point, we now can kick that group out and end with our beta keto form. Usually your nucleophile is going to be the same piece as the ester portion, so that way if that gets kicked out, you still have the exact same base. Some key differences if we look at the mechanisms for Claisen and aldol. On our Claisen, we actually have a good leaving group, so the negative charge can come down. On our aldol mechanism, when our oxygen has the negative charge, pushing that back down to carbon would have to have H- as a leaving group. So the incentive for here is, what are you going to make in your leaving group? Is it possible for you to kick it out?